In this lesson, we are going to go over end behavior and multiplicities, and this is part 1. So our goals today are to understand polynomial functions. That is what we are going to be using when we talk about end behavior and multiplicity. We are going to learn to identify the leading coefficient, leading term, and degree of a polynomial function, and then we'll be able to learn the end behavior of a polynomial function. Okay, so to get started, just some examples of polynomial functions. We have f of x equals 2x to the third power plus x plus 3, or something like f of x is equal to negative 5x to the fourth plus 4x squared plus x minus 1. F of x equals negative 10, x to the 10th plus x to the 7th plus 3x to the 4th minus 3x cubed plus 1. So these are just some examples. A couple things to note is that we've got x, and the power of x is a whole number. So 0, 1, 2, 3, it's not a fraction. We've got coefficients or numbers in front of x. We don't have any denominators in terms of like rational functions where we had like x plus 2 over x minus 3. Okay, this is what would make something like this a rational function. So on the next slide, I'm going to show you the general form of a polynomial function, and then we'll kind of break it down for what we need for this lesson. Okay, so a polynomial function, so it comes in the form f of x is equal to a sub n, x to the nth power, plus a sub n minus 1, plus x to the n minus 1, plus all these things in between a sub 1, and this would be x to the first power, and then a sub 0, which would be your constant. Okay, so the main takeaway from this is this term right here is the term with your biggest exponent or highest power. Okay, and this term here is a constant. Okay, and the way that this is written, so the powers are written in descending order or from biggest to smallest, and that's helpful because one of the things we're going to need to identify is the leading term. Okay, and the leading term is the entire term that has the biggest exponent. Next, the leading coefficient, so it's the number next to our variable with the biggest exponent, and n is what's called the degree of the polynomial, so it's the number of the biggest exponent. So if we look back, for instance, just in this first example, this is the leading term, 2 is the leading coefficient, 3 would be the degree. Okay, and the reason I can identify that right away is because the powers are written in descending order. So if they're not written that way, we can always rewrite them to get it into this form. Okay, so example 1, identify the degree, leading coefficient, and leading term of each polynomial. Let me get my pen. Okay, so we'll first check the powers are written in for f of x equals 2x cubed plus x plus 3. Oh, we just talked about that one. The powers are written in descending order. So the leading term is this entire first term with the biggest power. The leading coefficient is our number in front of the variable, okay, or our number next to the variable, and the degree is what's in the exponent there, the highest exponent, the number of the highest exponent. So this degree is 3. For the second one, we have f of x is equal to negative 5x to the fourth plus 4x squared plus x minus 1. So here is our leading term, okay, and we do need to include the negative. The leading coefficient is negative 5, and then our degree is the number of the exponent, which is 4, okay. For f of x equals negative x to the 10th plus x to the 7th plus 3x to the 4th minus 3x cubed plus 1, powers are written in descending order, which means that this first is our leading term. Our leading coefficient, notice there's no number here, but you can assume it to be negative 1. And our degree is 10. Okay, now we have f of x equals 6, so that is our leading term. It's also our leading coefficient, but our degree here would be 0. This is like x to the 0 power, and anything to the 0 power is just 1. Okay, on that last one, we have f of x is equal to x minus 2x squared. The powers are not in descending order, so you could either rewrite it or just note that our term that has the biggest power is our leading term, okay? But if you rewrite this, notice there's a minus sign in front of the 2, so this has to be negative 2x squared plus x, and now we can identify our leading term as negative 2x squared, our leading coefficient is negative 2, and our degree is 2. Okay. End behavior of a polynomial function. So now that we've talked about what polynomial functions are, we can get into end behavior. So end behavior is talking about how the graph behaves as x is very big or as x is very small. So basically it's how does this graph end up, okay? So x very big would be out here, x goes to positive infinity, x very small, as x goes to negative infinity, okay? And the reason that we just spent time talking about polynomial functions in our leading term is because the end behavior is determined by the leading term, which includes the leading coefficient and the degree of the polynomial, okay? So let's show some examples. So end behavior if we've got an even degree. So we have f of x equals x squared plus 4x plus 4. Here's what it looks like. It's our parabola, it's our U-shaped graph. Okay, and as our x gets very big, this is going to end up out here, and as x gets very small, okay, so our end behavior would look something like this. It's how it's going to end up, okay? We also have another even degree, but in this case, our leading coefficient is negative. So this will keep going. So as x goes to infinity, this is going to look like this. It's just going to keep going down. As x goes to negative infinity, it's going to keep going down. So our end behavior looks something like this. Okay, so that's telling us what the graph is doing when x is very big or when x is very small. Okay, knowing end behavior can help us graph, okay, or estimate what a polynomial looks like. End behavior for odd degrees. So we have f of x equals x cubed. So that's why the degree is odd, because we've got x cubed. Oops, I thought the pointer was on. Plus 2x squared plus x minus 1. Okay, so this graph ends up, as x gets very big, it ends up continuing to go up. And as x is very small or goes to negative infinity, it continues to go down and get smaller and smaller. So the end behavior is, oops, I'll write it like this. Okay, and the reason I'm writing it like this is you'll see these as part of the multiple choice when you're determining end behavior. Okay, so we have odd degree f of x is equal to negative x to the 7th minus 2x squared. Okay, so our end behavior is a little different. As x goes to infinity, this is going to keep going down. And as x goes to negative infinity, this is going to keep going up. Okay, so our end behavior would look something like this. Okay, so we're going to put this all together. These were just some examples into a table. Okay, so remember, this is our leading term test. So it's our term that has the biggest exponent. Okay, so if our degree is even, and this is our leading coefficient, is positive, our end behavior is going to look like it did in our example with our even degree when the leading term was positive. If our leading coefficient, again, this is also leading coefficient is negative, it's going to be frowning if we've got an even degree. Okay, with an odd degree, it's kind of doing this squiggle, and then it goes the opposite way if our leading coefficient is negative. Okay, so this is a table that you'll want to make sure that you have in your notes. It's how we are going to determine end behavior. So example 1, describe the end behavior of the graph of the polynomial function, or another way you might see this is find the correct end behavior diagram for the given polynomial function. So we have f of x is equal to 8x to the 5th plus 4x cubed plus 2x squared plus 1. So our leading term is 8x to the 5th, and our degree is odd. Okay, so that automatically kicks out a and b. If we've got an odd degree, it's going to squiggle up or squiggle down. Okay. And since our leading coefficient is positive, we are going to see graph C, okay, or the diagram C. Okay. Next, example 2, same instructions. F of x equals negative x to the 4th plus x squared plus 1. Powers are written in descending order so we can identify our leading term. Our degree is even, so it's going to smile or frown. So I'm going to cross off C and D right away. Okay, and our leading coefficient is negative, so it's going to frown. So the correct answer here is B. Example 3, same instructions. F of x equals x squared minus 3x to the 7th. These are not written in descending order, so you could say, okay, well, I know that's going to be the leading term, or you could rewrite it as negative 3x to the 7th plus x squared, keeping their respective signs. So I have an odd degree, so it's not smiling or frowning, it's going to squiggle. And then the leading coefficient is negative. Okay. So the correct answer here is D. Next, example 4. Again, it's not written in descending order. The powers are not written in descending order. So we can rewrite this as x to the 10th plus x squared minus 6x plus 4. So I have my leading term. the degree is even, so we're going to be talking about smiles or frowns. And then the number in front, there's no negative in front. The number in front is just 1 if there's nothing written there. So this is going to smile. The correct diagram is A. Okay. There's one more thing that we can do. We can use the leading term test to match the graph of a function. So remember, we can determine if it's an even or odd degree from the leading term, and then if it's a positive or negative leading coefficient, again from the leading term, from the leading. Oh, that should say leading term. Okay. So use the leading term test to graph the function. So what you'll be able to do is you'll be able to match it to something different. But here I'm just going to draw a rough sketch. So my leading term is negative x to the 6th. My degree is even, okay, but my leading coefficient is negative. So I know that my end behavior is going to kind of frown at me, okay? So if I were just to draw a rough sketch, now this isn't dealing with x-intercepts or zeros or anything like that. We'll get to that in the next lesson. It could do something like, okay, I don't know what it does in between here. And this area I circled in green, but I do know that as x goes to infinity, the y values are going to get more and more negative, and same thing as x goes to negative infinity. Okay, but like I said, you'll have a graph to match this too. Use the leading term test to graph the function. So we have f of x is equal to 3x to the 5th plus 1/4 x squared minus 4. My leading term is 3x to the 5th. My degree is 5, and my leading coefficient is 3. Okay, so my end behavior is going to look something like this. It's going to squiggle. Okay. And so when we're graphing this, it could do something like this. Okay, so make sure that whatever graph you're matching it to matches the degree, the end behavior, and what's happening with the leading coefficient, which tells us the end behavior. Okay. Use the leading term test to graph the function. Okay, so this one is written in factored form for us. So there are a couple of options. You can multiply this all out. So if you were going to do that, you would start by doing x minus 3 squared, which would require FOIL. Okay, and then multiply by x plus 1. But remember, we're just concerned with the leading term. Okay, so with the leading term, from here we would get x squared plus a bunch of stuff times x plus 1 plus a bunch times x plus 1. Okay, and then if we were to distribute, our leading term would come out to be x cubed and then plus a bunch of stuff. So you can look ahead and look at what the multiplication would look like, okay, in order to determine what our leading term is going to be. Okay, so we've got our leading term is going to be x cubed, so it has an end behavior as a squiggle, so this graph could go something like this. Okay. Thank you for watching. If you have any questions, feel free to reach out to me.